Here we are going to prove that for every even integer n, dn has a subgroup of order 4. Okay, so here dn denotes the set of symmetries of n-sided regular polygon. Okay, so we have to prove the existence of a subgroup of order 4. Okay, in one of the earlier videos we had discussed a result that let G be a group and let there be at least let G have two elements of order 2 at commute. Okay, then G has a subgroup of order 4. In one of my earlier videos, I had proved this. If we are taking alpha and beta to be the elements of order 2, then identity element alpha, beta, and alpha beta is going to be the required subgroup H of order 4. Okay, so here our aim will be consider Dn, okay, and then we will produce two elements of order 2 in Dn, okay, such that they must commute. Okay, if we have done that, then if we give that elements, then we are done. Okay, so consider Dn. Okay, in that we know that given that n is even, okay, n is given to be even, then definitely we know that rotation by 180 degrees is an element in Dn, right? Because in one of the earlier videos, I had also shown that if n is even, R180 will be there, and R0, rotation by 0 degrees, which is nothing but the identity element, and R180 degrees, okay, these two will be there in the center of Dn. Okay, I had proved this in one of the earlier videos, right? So here we have got an element r 180 degree, and of course this is of order 2, and of course you can imagine that, right? We rotate by 100 degrees and again rotate by 180 degrees, so it will be rotation by 360 degrees, which is equivalent to rotating by 0 degrees, and so r180 has order 2. Okay, and this R180 in Dn will commute with every other element. Okay, now pick an element F which is a reflection. Okay, which is some reflection. I am not giving any additional constraints on this. Let F be any reflection in Dn. Okay, now F also has order 2, right? Any reflection will have order 2. In particular, F also has order 2. Now, instead of R180, I'll be just denoting it as R. Okay, consider RF. Okay, again, RF is an element of Dn. Okay, now what will be the order of RF? Here, consider RF. We also proved that in one of the earlier videos, I had proved that RF is also going to be a reflection. So its order also must be 2. Okay, so how did we prove that? Just to summarize this, suppose RF is a rotation, then I can we can cancel r from both sides, and or I can just multiply by r inverse. Like suppose rf is equal to some rotation, say r dash, then we will have f is equal to r inverse r dash, and this r inverse is also rotation, r dash is also rotation, and their composition will also be a rotation. So that means f will have to be a rotation, so that is a contradiction, so that is not possible. So rf cannot be a rotation, rf has to be a reflection, and we know that RF is a reflection and every reflection will have order 2. So RF is also having order 2. Okay, and we know R. Here R is rotation by 180 degrees. It commutes with every element because R 180 degree is there in center. So it commutes with every element. So I have produced two elements. What are they? F and rotation by 180 degrees. Both of them are of order 2 and they are commuting. So definitely it has a subgroup of order 4. Okay, so using this, I have proved the existence of a subgroup of order